Hey guys, welcome back to my channel where we explore interesting math problems. Today, we'll be looking at not one, but two problems from the 2023 Canadian Math Contest Euclid, which is designed for 12th graders. The contest has 10 questions, with the questions ordered roughly from least to most difficult. We'll be looking at question 8 today, which has parts A and B, both of which we will solve. So the question for part A reads, suppose that triangle ABC is right-angled at B and has AB equals n multiplied by n plus 1 and AC equals n plus 1 multiplied by n plus 4, where n is a positive integer. Determine the number of positive integers n less than 100,000 for which the length of side BC is also an integer. Let's start with a visual. So we know that side AB is n times n plus 1 and side AC is n plus 1 times n plus 4. By the Pythagorean theorem, we have this equality. Plugging in what we have and simplifying, then taking the square root to get BC, and further simplifying, we end up with BC is equal to 2 times n plus 1 times the square root of 2n plus 4. Since the question asks for the number of n for which BC is also a positive integer, this part of the square root must be an integer too. This means that the question is essentially boiled down to finding the number of n that makes the square root a positive integer. So we let k be equal to the square root of 2n plus 4. Then squaring it, we get this. So we know that the square of an integer goes something like 1, 4, 9, 16, 25, and so on. However, since the given constraint said that n has to be a positive integer and that BC also has to be a positive integer, the only k-squared that 2n plus 4 can produce will be an even number from this list that is greater than 4. It has to be even because 2 multiplied by n would always produce even number, plus 4 is still an even number, and it has to be greater than 4 because if 2n plus 4 is equal to 4, then n has to be 0, but the constraint said that n has to be an integer, positive integer, so it has to be an even integer that's greater than 4, which is starting from 16. So because 4 is 2 squared, we know that this limits the possibility of k squared to starting from 4 squared, and so on. So now we have this sequence of even integers with their squares of what k squared could equal to. Now to find the upper limit of this sequence of possible k's. We know that n is less than 100,000, and that 2n plus 4 will be less than 200,004. Substituting in k squared for that and squaring it, we know that k has to be less than 447, and because k squared has to be an even integer squared, this means that the biggest even integer less than 447 will be 446 squared. Ignoring the squares in this sequence, we can represent the base of this sequence with 2x plus 2, and equating that with 446, and solving for it, we know that there are 222 terms in this sequence. And since we know all terms of this sequence satisfies the condition of making this square root an integer and thereby making BC also a positive integer, the number of positive integers of n less than 100,000 to make BC an integer is 222. Now on to part B of the question, which is completely unrelated to part A, but I thought that I would combine them just because both of them are relatively simple to explain. So the question for part B reads, determine all real values of x for which the square root of log 2 of x multiplied by log 2 of 4x plus 1 plus the square root of log 2 of x multiplied by log 2 of x divided by 64 plus 9 equals 4. We can first simplify this equation by using logarithmic laws to separate the 4 from the x and the x from the 64. Over here we use the product rule, while this uses the quotient rule. So I'm not going to explain about how the rule works, as I'm assuming that most of you would know this already, but I've attached a link below for those of you who need to brush up on some logarithmic concepts. As we can see, now we have a lot of log 2 of x everywhere in this equation. So just to simplify it, we can let k equals to log 2 of x, and we're left with this. Multiplying it out, we get this. And if you're familiar with quadratics, you will notice that both of these expressions within the square root sign are perfect squares. Specifically, this and that. You may be tempted to think that when we have a square and a square root, we can just directly take this expression inside the square and the square root. However, that's not true, because x plus 1 and x minus 3 could be a negative number, and if you square it, it would be a positive number. But when you take the square root, you would get the positive version of that number. So in either case, you have to add an absolute sign on both of it. And we can then use casework to solve this, since different values of k would determine whether we need to put a negative in front of each expression when we get rid of the absolute sign. And just to clarify, let me explain how that works. So if the particular value that we chose for k means that k plus 1 is a negative number, then if we get rid of the absolute sign, we need to put a negative in front of that number in order to make it negative, since absolute signs make all numbers positive. So for case 1 is when x is less than negative 1. This would make both expressions inside the absolute sign negative, so we put a negative sign in front of both of them. And solving for it, we get that k is equal to negative 1. And don't forget that k is actually equal to log 2 of x. And solving for that, we get that x is equal to 1/2. And on to case 2, where k is between negative 1 and 3. In this case, k plus 1 would be positive, so no negative sign needed. But k minus 3 would be negative, so you need to put a negative sign. And solving for it, you would actually get 4 equals 4, which is a true statement. And what this means is that all values of k within this interval will make this expression true. So again, we substitute for what k equals to, and solving for x, we get that x is between 1/2 and 8. And on to case 3, where k is greater than 3. Both expressions are already positive, so no negative sign needed. And solving for that, we get k is equal to 3. And again, substituting and solving for x, we get x equals to 8. So now we just need to put all three of these values together. So you notice that x equals to 1/2 is just the same as the lower bound of this, and x equals to 8 is equal to the upper bound of this. So when you put them together, you just get x is greater than or equal to 1/2 and less than or equal to 8. And that concludes question 8, both part A and B of the 2023 Euclid examination. I hope you enjoyed this video, and I'll see you next time.